Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Ahmad Nauman, and today in this lecture we will have an overview of the magnetic properties of advanced materials. So magnetic properties doesn't only mean whether a material will make a good or bad magnet, but it is also includes whether a material will be attracted or repelled by magnet. So it comes under the magnetic properties of a materials. And magnetism actually arise from moving charges that can be an electrons, or that can be caused by the nucleus. So basically it arises from moving charges such as electric current in a coil of wire. And these magnetic properties also arise from the spin and orbital angular momentum of the electrons contained in a compound. So we will discuss it in next slides in detail. And we know that atoms are made of charged particles, which are protons and electrons, so which are moving constantly. Electrons are revolving around, so both protons and electron actually can create or can result in magnetic properties of a material. So magnetism or magnetic properties of materials can be induced or can be related with different properties in or different phenomena in a compound. So we will see those processes which create magnetic field in an atom, and broadly speaking we can say that magnetic properties, the intrinsic magnetic properties, are induced by the following three phenomena. First is the nuclear spin. So some nuclei, for example hydrogen atom, which have a net spin, can create a magnetic field. Besides nuclear spin, we know that electron also spin around their axis, and because of that spin it can also result in the generation of magnetic field. And the third and the most important process which create magnetic field is the motion of electron around the nucleus. So that also results in the formation of magnetic field, and normally this contributes to the magnetic properties of a material. Another very important terminology which we should study when we are talking about magnetic properties of material is Weiss domains. So what are the Weiss domains? So every magnetic material is divided into magnetic domains called Weiss domains after a French physicist who predicted their existence theoretically in 1907. So first of all, the question is, what is a domain? A magnetic domain is a region within a magnetic material in which the magnetization is in a uniform direction. मैग्नेटिक डोमेन वो एरिया है, वो रीजन है किसी भी स्पेसिफिक मटेरियल के अंदर जिसके अंदर उसकी मैग्नेटाइजेशन जो होती है वो सेम यूनिफॉर्म डायरेक्शन में होती है, एक ही डायरेक्शन में होती है, which means that individual magnetic जो moments हैं of the atom, they are aligned with one another and they point in the same direction. So this is what we call magnetic domain, and that is also we call it Weiss domain because it was first described by the French physicist Weiss in 1907. So when we expose magnetic material to an external magnetic field, what happens कि जो हमारे पास जो domains होते हैं जिनके अंदर जो magnetization होती है that is in same direction but they are in different patches. So in one part of a material they are although in the same direction the set of magnetization, but in another region they can be in also arranged but they are pointing in different direction. So when we apply a magnetic field, what happens that these boundaries of these domains, they actually shift and they try to arrange themselves according to the applied magnetic field. So when we increase the magnetic field, more and more of those magnetic fields actually try to arrange themselves according to the applied magnetic field. This is the same when we see in the previous animation in which मैग्नेटिक फील्ड इज अप्लाइड और उसकी जब स्ट्रेंथ इंक्रीज होती है तो क्या होता है कि जो इंडिविजुअल मैग्नेटाइजेशन होती है, जो मैग्नेटिक मोमेंट होता है वो शिफ्ट करता है टुवर्ड्स द डायरेक्शन ऑफ अप्लाइड मैग्नेटिक फील्ड. सो same happens and these magnetic domains actually try to arrange themselves in the direction of the external magnetic field, and more domains shift to towards the magnetic their direction towards the direction of magnetic field with increase in the strength of the magnetic field, and ultimately it happens that all of the domains are actually magnetized in the direction of magnetic field, and that material is then saturated, which means it attains the maximum magnetization, and thus we call it magnetically saturated. So जैसे हमने डिस्कस किया in the previous slide, so we can see here the top figure that we have different domains के different areas जहाँ पे जो magnetization है वो same direction में. For example, if we see in the top image on the left side, so we see that all the domains are in the upward direction, and if we see on the right side we see that all are in the their direction is downwards. And also we can see there are 6 different domains in which the individual magnetizations are uniform, but they all domains actually differ from each other. So what happens कि जब हम नीचे वाली डायग्राम देखते हैं कि जब हमारे पास जो नॉर्मल जो मटेरियल होता है when we don't have any applied magnetic field, so these domains are there, so there are not uniformly arranged all the domains. So when we apply magnetic field, so what happens, as you can see in the second center image in below, that some of the magnetic moments try to arrange themselves according to the magnetic field, and when we keep on increasing the strength of applied magnetic field, more and more domains arrange themselves according to the applied magnetic field. And if you see the last image on from the bottom, we see that all of the magnetic domains and are arranged according to the direction of the magnetic field. So this is actually known as the saturation of the magnetic material. So this is the representation of actually the bias domain which we discussed in the previous slide. So that was the introduction to magnetization and extent of magnetization and bias domains, and now we will discuss about the different types of magnetic substances. So when we place a material in magnetic field, so it give response in different ways. So based on the different responses of different materials to the applied magnetic field, we put them into different categories. So now we will study those types of magnetic substances. So broadly speaking, we can categorize magnetic materials into diamagnetic substances, paramagnetic substances, ferromagnetic substances, antiferromagnetic substances, and ferrimagnetic substances. So in diamagnetic materials, for example, copper, silver and gold atoms have no unpaired electrons. Thus because if they have no unpaired electron, which means जो electron होंगे they will be in the form of pairs. So as we discussed previously, if we don't have unpaired electron, the pair of electron will have magnetic moments in opposite direction, and thus they will cancel out their magnetic moment. So thus in diamagnetic substances which have no unpaired electrons, the electrons will cancel out their magnetic moment, and we will have zero net magnetic moment. And these diamagnetic substances are mostly weakly repelled when they are placed in a magnetic field. जब हम magnetic field apply करते हैं to a diamagnetic substance, then what happens कि the magnetic moment of electron, they actually align themselves in the opposite direction of the applied field. So next type is we will discuss is paramagnetic substances. So when a paramagnetic material is placed in a magnetic field, the magnetic moments of the atoms align themselves along the direction of applied magnetic field. So in contrast to the what we see in the diamagnetic substances, in paramagnetic substances जो when magnetic field apply करते हैं, the magnetic moments of the atom they actually align themselves as per the direction of the applied magnetic field. However, जब we remove the applied magnetic field, what happens कि these materials do not retain the magnetic moment and they come back to their original state. Thus in paramagnetic materials, जैसा कि हमारे पास एग्जांपल है ऑक्सीजन है, कॉपर 2 प्लस है, आयरन 3 प्लस है, मैग्नीशियम है, they mostly contain one or more unpaired electrons which actually cause their magnetic moment. And when we talk about the properties of magnetic substances, they are weakly attracted by the magnetic field because they have a very limited number of unpaired electrons. So the third type of magnetic materials we have are known as ferromagnetic substances. So when ferromagnetic substances are placed in a magnetic field, so their magnetic domains actually align along the direction of the applied magnetic field. But जो ferromagnetic substances होते हैं, they are different to the diamagnetic substances and paramagnetic substances in the fact that जब आप इनको magnetic field apply करते हैं, they do align with the direction of applied magnetic field, or even if you remove the applied magnetic field, so still the ferromagnetic substances retain some of the magnetization. So that's why we also call them the permanent magnets. And mostly in ferromagnetic substances, the spin होती है unpaired electrons की, they are mostly parallel to each other. And the examples of some examples of the ferromagnetic materials include iron, cobalt, nickel, and chromium dioxide. So in antiferromagnetic materials, for example, we have manganese oxide, we have cobalt oxide, nickel oxide, or copper chloride, which are given on the screen. So they show that the antiferromagnetic materials are mainly the compounds of two or more different atoms that occupy different lattice positions. So the important thing which you should be you should know that the antiferromagnetic substances actually have unpaired electrons, but the atoms which have magnetic the two atoms which have magnetic moments and that are equal in magnitude and they are in opposite direction, so what happens that they cancel out each other. So what are antiferromagnetic substances? In समरी हमारे पास जो है वो मैग्नेट ये कंपाउंड्स होते हैं डिफरेंट मटीरियल जिनके अंदर दो डिफरेंट की तरह के आइटम होते हैं. फॉर एग्जांपल कॉपर है, क्लोराइड है, निकल है और ऑक्सीजन है. सो व्हाट हैपन्स दैट दे हैव अनपेयर्ड इलेक्ट्रॉन्स एंड दे हैव देयर मैग्नेटिक मोमेंट्स, बट व्हाट हैपन्स इज कि जो उनकी डायरेक्शन होती है वो एक दूसरे की डिफरेंट होती है और उनका जो मैग्नेटिक मोमेंट होता है उसका मैग्नीट्यूड ऑलमोस्ट सिमिलर होता है. दैट्स वाई they cancel their effect and result in the zero net magnetic moment. For example, you can see in this diagram कि हमारे पास जैसे आप देखें कि जो first diagram है, it has the magnetic moment in upward direction, lower direction, next is the downward direction, same is upward, downward, and that continues. So what happens is कि the magnetic moment of these two different atoms which are in opposite direction and have almost similar magnitude, they cancel out the magnetic moment of each other, and thus we have a zero magnetic moment and it doesn't show the magnetic properties. We have another kind of ferrimagnetic magnetic substances which we call as ferrimagnetic substances. So they similar to the antiferromagnetic substances, these ferrimagnetic materials are also made of atoms of they are compounds of different atoms which reside on the different lattice site, and they also have the anti-parallel magnetic moments. They have magnetic moments whose direction is different. But जो मेन डिफरेंस है यहाँ पे फेरी मैग्नेटिक मटीरियल का और एंटी फेरोमैग्नेटिक मटीरियल का वो ये है कि एंटी फेरोमैग्नेटिक मटीरियल्स दे हैव टू डिफरेंट एटम विच हैव मैग्नेटिक मोमेंट जिनकी डायरेक्शन डिफरेंट होती है और वो एक दूसरे को कैंसिल आउट करते हैं. हाउएवर इन फेरी मैग्नेटिक सब्सटेंसेस although they have magnetic moments in opposite direction, but the magnitude of the magnetization is different. Their magnetic moments magnitude is different. So for example, for iron and magnetite की बात करें Fe3O4 की, so for example iron has a higher magnetization as compared to the oxygen. So though they will be in opposite direction, so they will cancel out each other's effect, but they cannot completely cancel out each other effect because their magnetization or magnitude of magnetic different is different. So in these materials the magnetic moment do not cancel out since they have the different magnitude, which result in a net spontaneous magnetic moment. This we can see in the following diagram. इसमें देखें कि ये हमारे पास जैसे फेरीमैग्नेटिक सब्सटेंसेस हैं, they are compound of two atoms. So here we can see we have in the first diagram we can see that the two atoms have magnetic moment in opposite direction, but the magnitude of magnetization is different. So that's why although they cancel out each other, but they cannot completely cancel out each other. So that's why there is still remains a magnetic moment. Similarly, we can see the second diagram, which is maybe give you better idea that we have magnetic moment shown for different atoms, which are two different atoms here, and we can see that their magnetic moments are in opposite direction. They are anti-parallels, however their magnitudes are different, so they partially cancel out each other's effect, but still a net magnetization remains. So such materials are known as ferrimagnetic substances. So now let's start with the magnetic properties of advanced materials. And mostly जो हमारे पास inorganic solids हैं, they affect they exhibit different magnetic properties other than diamagnetism, so they are important for their use in different applications. And we know that to be for a material to be a magnetic, they should have unpaired electrons in their valence shell. So normally the transition metal elements or lanthanides, they have unpaired electrons in their D and F shells respectively, so they are mostly used for the application where magnetic properties are required. We already discussed कि जो unpaired electrons होते हैं, they induce the magnetization in materials through different way, either they are through spin or their orbital motion. So they are really important for a material to be magnetic in nature. Or some of the magnetic oxides, one of the common application है magnetic materials that is used in the transformers जो आपके use होते हैं बिजली के. So their core is actually made of magnetic material, which is MgFe2O4, and there are some other magnetic oxide as well which are used for that purpose nowadays. And also these magnetic oxide, other than the transformer cores, they are also used in the recording and information storage devices. जैसे हमारे पास हार्ड डिस्क वगैरह होती हैं कंप्यूटर की, तो उसके अंदर भी जो है इनको यूज़ किया जाता है मैग्नेटिक ऑक्साइड्स को. Another very important application of magnetic materials in biomedical research and one of the most hot topic is the use of nano carriers which are based on magnetic materials for the anti-cancer therapy. So there are many other applications in which magnetic materials are nowadays used in the biomedical research and this is a very rapidly growing area of the research nowadays. However, when we talk about the use of magnetic materials for different applications, so the understanding the correlation between a magnetic property of a material and its structure or nanostructure is really important for potential applications. Depending आपने कहाँ पे किसी magnetic material को use करना है, so on the basis you have to synthesize those materials with a specific nanostructure, and that will actually enhance the efficiency of those substances for a particular application. For example, when we talk about platinum or gold, so we know that they are diamagnetic substances, so they are non-magnetic, but there are certain applications in which if we use platinum and gold, so they can be really beneficial if they can have magnetic properties, but we know that they are diamagnetic, so we try to make them magnetic. And there are different techniques which are used for making them magnetic, but one common technique is to reduce their size into the nano level. So if we make the nanoparticles or nanocrystals or whatever nanowires, so there can be multiple structures which are possible, so they can have the magnetic properties. So this is really important, the relation between the magnetic properties and the nanostructure of the material, and that will totally depend where we gonna use those materials. So we will synthesize them in that way, or we will make that structure of the material. And one of the important thing that we should remember, that non-ferromagnetic substances including zinc and platinum and some other materials, so they are non-ferromagnetic, they are diamagnetic, so they may exhibit even ferromagnetic like behavior when they are in the nano range. So this is a really important point, that we can change or we can manipulate the properties of magnetic for non-magnetic materials and make them magnetic only through reduction of their size. And another common way of inducing magnetic properties in non-magnetic material is the surface modification. Okay, one possibility is that we reduce the size of the material so that they show ferromagnetic behavior. Another possibility is that we cap those surface or nanoparticles or the materials with some specific chemical compound or chemical species which make them magnetic. And this process of capping the materials with appropriate molecules is really important, that it can manipulate the characteristic of materials and especially the magnetic properties of that materials. So we can get the ferromagnetic properties from those materials which are actually diamagnetic in nature through surface modification using different chemical compounds. Advanced materials with tuned electrical and magnetic properties are the goal of all material scientists. So there are different applications where magnetic materials are used, their electrical materials are used. In some cases, for example, if we have a material which is a semiconductor material and however it is not magnetic, so there are many applications. For example, in spintronics, के जहाँ पे ऐसा मटेरियल which shows both semiconducting and magnetic behavior, they are really important. And for that purpose जो है उसको जो हमारे पास मटेरियल होते हैं, we tune them, we manipulate them through some chemical modification, some size reduction, and we get the desired properties from those materials for those specific application. So by manipulating the magnetic properties of different advanced materials or different materials, we can enhance the efficiency of different devices. For example, electronic devices, we can enhance the performance and efficiency of the hybrid जो हमारे पास electric cars आ रही हैं, उनकी efficiency we can enhance that. And also we are having some data storage devices, so we can also enhance their efficiency and we can use them in a better way and more efficient way. So the magnetic materials are really important for all of these applications. So a good control of their magnetic properties through their size reduction or capping actually determines how efficiently we can use those magnetic materials for that certain application. Let's take another example. So the strongest permanent magnet which is currently used is the composite material of neodymium, iron and boron, which was made in around 1984, and after that it has been used in many applications. For example, in the magnetic storage devices, या जो हमारे पास electric जो vehicles होती हैं, their motor is actually, they contains that neodymium, iron, boron composite magnets, because Currently, these are the most strongest permanent magnets available. So these are also used for magnetic resonance imaging. Beside the hard disks, they're used in the magnetic storage devices, and they are also used for sensors and high performance motors for hybrid electric cars. But a problem is that although they are they are very strong permanent magnet, but still at high temperature, because when we are dealing with the cars or vehicle engines, so their temperature is very high over there. So their efficiency is actually still suffers at high speeds and high temperature. So that is a current problem which the scientists are having while working on the electrical vehicles. So how can we solve that issue? Okay, how we can कैसे हम इसको रोक सकते हैं कि जो इसकी कोर्सिविटी है वो रिड्यूस ना हो एट हाई टेम्परेचर? हाउ कैन वी मॉडिफाई दैम? सो what is the solution for that? So one of the first step which we have to take to improve their properties is to know them or know their characteristics at the very nano level. So for that, these days some very efficient electron microscopes which have the resolution of atomic level, they are being built, which are available and help the scientists to study these materials at the atomic level, especially these kind of composite materials for their high functional applications. And the use of these very hi-fi techniques is actually helping the scientists and the material researchers to understand how they can improve their properties and how they can manipulate their properties for a specific application. We will take an example. For example, we have lanthanum ferrite and the strontium titanate. So this composite material actually have both of them, both lanthanum ferrite and the strontium titanate have different properties, but the interface where they both join, if we look at the subatomic level, so there are some specific interaction on the interface of both these, which result in specific properties which are not found in both of these materials. However, at their interface they exhibit very special properties which can be used for specific application. So that was different applications of the magnetic materials, especially for advanced magnetic materials which are used for certain advanced or high-fi application for electric vehicles and those things. Overall, if we see, there are many materials, there is a vast variety of advanced materials which are used for certain magnetic application, whether it is for data collection or processing, or for data transmission, storage, or display information, or electrical vehicles. So there is a huge variety of magnetic materials or advanced magnetic materials which are used nowadays in the different industries. Thank you so much. That's all for today, and take care. Allah Hafiz.